In the last class, we have discussed about the constant current source, current mirror circuit. So for improving CMRR, today we are going to discuss about active load for improving CMRR. So in this active load, we are going to consider current mirror circuit in the place of emitter resistance RE. In the place of emitter resistance RC. So here you can see that circuit. In the place of emitter resistor RC, we are going to use this constant current source. So we are using a constant the current mirror circuit which has very low DC resistance and high AC resistance. So this offers high resistance for AC signals and offers low resistance for DC signals. So such that such a mirror circuit we are going to use here. So it acts as an active load. Nothing but with the help of active elements we are going to improve. We are going to introduce here. So because of that, it is going to act as a active load. It is going to act as active load. Here, if the signals, the input signals VS1 and VS2 is equal to 0, we can see that yes, Q2 and Q1 are matched transistors. Then the currents I1 and I2 will be in equal magnitude. So which is equal to the half of emitter current. So emitter current, that is nothing but this is the current source, current mirror. So here we have used. So half of this current mirror current is equal to this I1 and I2. So here from this circuit, I1 is equal to I2 and I, which is equal to I. So I is the current flowing in this transistor. Here you can see this I. So from this equation we can write IL is equal to I minus I2. So here the output current we are going to take from here, the collector terminal of this Q2 transistor and the collector terminal of this Q4 transistor, where these two is met, we are going to take the output. And here this current is going to flow in this direction, as the current coming from this Q4 transistor collector is I, and this is going to be deviated into two parts. So that is nothing but IL and I2. So IL is going to flow towards the load and I2 is going to flow towards the Q2 transistor. So from this diagram we can write that the current IL is equal to I minus I2, so which is equal to 0. The net current is equal to 0. So when VS1, from this we see that as VS1 is increasing when compared with the VS2. So if VS1 increases when compared with the VS2, then the current I1 increases whereas I2 decreases. So VS1 increases, I1 is going to increase and I2 is going to decrease. So this will balance the current. So I1 plus I2 is equal to IE, which is constant. So we can say that here if I1 increases, I2 is going to decrease. Maintains the constant current IE. So here IE is maintained constant. So here you can see that. So I is equal to I1, hence due to the current mirror action. So due to the current mirror action, I is equal to I1. So as we know that current mirror, the entering current is equal to the leaving current. So I is equal to I1. Current mirror operation, nothing but. So if VS1 increases or VS2, I1 increases, I2 decreases. Since I1 plus I2 is equal to IE. So in the same manner, if VS2 increases, then I2 is going to increase and I1 is going to decrease. So in this way, it provides a constant current IE. So this is one of the method for improving CMRR. So this is the one of the method for improving the CMRR. So next, so we are going for level translator circuit. Next, we are going for this level translator circuit. So what is this level translator? So up to now we have discussed about, as we have discussed in the first class itself, So op amp is nothing but op amp consists of mainly four blocks. So in that four blocks, the first two blocks constitutes of a differential amplifier. So two differential amplifier, first two block consists of a two differential amplifiers, and the third block is nothing but it is a level translator circuit. So as we have discussed up to now is a differential amplifier circuits, and how to improve the CMRR for differential amplifier we have discussed. We are also discussed about that, and we are coming to the third block, that is a level translator circuit. So this level translator circuit, you can see. So what is this level translator? Why we are going to use this level translator? Now we are going to see. So yeah, up to now we have discussed the two blocks, that is a differential amplifier circuit, and which are directly coupled. So as op amp is operated on DC, we are not using coupling capacitors between the two stages. That is what we have discussed about first stage and second stage. So first stage is a differential amplifier and second stage is also a differential amplifier. So which are directly coupled. So because of this direct coupling, the DC level is going to increase from stage to stage. So here you can see the DC level is going to increase from stage to stage. There will be introduction of DC from stage to stage. So because of this introduction of DC level, so the signal will not maintain at a zero level. So it is going to shift by some DC voltage. So this can be overcome. So this can be maintained at zero level by using this level translator. So this level translator, which keeps the level of the DC signal, level of this signal, that is the DC level of the signal, to zero. So this DC, if it does not use this level translator, then this DC is going to distort the signal. So that is op amp performance will be distorted because of this DC. So because of that, we are going to use here a level translator, which keeps the quiescent level of 0 volts for zero input signal. So we are using a level shifter or level translator. It is also called as shifter or level translator. So here you can see these three circuits, three different circuits of level translator. So the basic circuit here you can see. So here we are using a emitter follower circuit. So here this is an emitter follower circuit in which the input is given to the base terminal, and output is going to taken at the emitter terminal of the transistor, and it is grounded through our resistor R. So and VCC is given to the collector of the transistor. So from this circuit diagram, so if you observe the output voltage, so if you take the difference between the output voltage and input voltage, nothing but if you are going to write the equation for the output voltage, V naught is equal to V in minus drop across this base to emitter resistor. Drop across this base to emitter, voltage drop across this base to emitter. So whatever the input signal given, that the difference between the input signal and base emitter drop will be obtained as a output. So with this, with that equation, we can write that V naught minus V in is equal to minus VBE. So V naught is equal to V in minus VBE, nothing but V naught is equal to V in minus VBE. So V in minus VBE means, if for example V in is plus 5 volts, VBE is 0.7 volts, 5 minus 0.7. So that will be around 4.3 volts. So V naught is 4.3 volts. So like that, the level is going to be adjusted. So whereas, so this, because of this VBE, there will be a shift in the level will be adjusted. V naught is equal to V in, but VBE, because of this VBE, the level will be somewhat for high values of voltage signals, there will be no distortion. There will be no any objection for that. So, but if we consider the low voltage values, but in electronics we are going to consider for for amplifier applications. So we are going to use a millivolt signal as an input signal. So if you use a millivolt signal as an input signal, then 0.7 volts is very high voltage when we are going to compare the distortion. So because of this, so we are going to use another circuit, mm, that is this circuit B. So here we are going to introduce a resistor R1 and R2, and we are going to take output between these two resistors. Between these two resistors, what will happen? We are going to see now. The output is taken at the junction of two resistors, that is R1 and R2. So now V0 is equal to V0 is equal to, that is input voltage minus voltage between the base to emitter. This is here the VB is nothing but voltage between the base to emitter into R2 divided by, that is voltage division rule. So voltage into R2 divided by opposite resistance, that is R2 divided by total resistance in that path, that is R1 plus R2. So here we can see that V0 can be controlled by using R1 and R2. So in this circuit, the drawback is, so V0 cannot be controlled. That is VB is constant. There is no adjustment of this. So VB is constant. There is no adjustment. We cannot make any adjustment here. But here, so we can adjust the value of V0 by changing the values of R1 and R2, because here you can see from this equation, the V0 is going to depend upon the resistance values R2, R1 and R2. So by changing these resistance values, so we can adjust the value of V0. So in this way, we are going to shift the level or adjust the level of the signal, DC signal. So this can also be another circuit. So C is another circuit, that is here we are going to use a current mirror circuit. So here we are going to use a current mirror circuit. In the place of this, so here this is the transistor and R1 resistor. As it is, we are going to use the R1 resistor. In the place of R2 resistor, we are going to replace it with the current mirror. That is nothing but I is the, so I is the entering current, I is the leaving current. So this I and I are both are equal, which maintains the constant current. So see here, the shift is given by, so from this circuit, we can write that the shift is given by V0 minus Vi is equal to minus VBE plus I into R1. So V0 minus Vi is equal to minus VBE minus of VBE, voltage to base emitter voltage. This is for this transistor, minus of VBE plus I into R1. So this, the current flowing through this R1 is nothing but I. So I into R1, drop across this R1. So V0 is equal to Vi minus VB minus I into R1. So due to this, there is no AC attenuation. So because of using this current mirror, so there is no AC attenuation due to high resistance. So by this, so we can maintain the DC level. So another circuit is also there, that is voltage multiplier circuit. So this is a voltage multiplier circuit. Here you can see this is the input transistor what we are going to use for shifting the level. So which is for which we are going to give the input V in, and this is the Q1 transistor, this is VBE, and to this emitter, so we are going to connect this circuit. So we are going to take output between the transistor Q2, between the collector terminal and emitter terminal of Q2 transistor. So how this circuit is going to work, now we are going to see. So this circuit is also called as voltage multiplier circuit. Voltage multiplier. Why it is called voltage multiplier, we will see here. So here I is the emitter current of Q1 transistor. That is I is the emitter current of Q1 transistor. So I is the current of Q1 transistor. From Q1 transistor, this current is going to come. So current through R2 is I by neglecting the base current of Q2. So current through R2, the R2 resistor current is also I. So we are going to neglect here base current. So and then we can say that the same current I is going to flow through R1 and R2. So by neglecting the base current of I1, now we are going to consider the voltage between A and B. So A is the point here we have taken, and B is the point here we have taken. So we are going to measure the voltage between these two terminals, that is A and B. So if you write the equation for that, so VAB is equal to I into the, so same current is going to flow through R1 and R2. So I into R1 plus R2. So this is the equation number 1. Keep it aside. And now we are going to write the KVL for the base emitter loop of Q1. So now Q2, sorry, base emitter loop of Q2 transistor. So now, so this is nothing but base emitter loop of Q2 transistor. This is the part we are going to write the KVL. So minus I into R2, the entering current is nothing but I into R2. So the current flowing through R2 is nothing but I. So we are going to go in this direction. So we are going to opposite direction of I. So we are going to write minus I into R2. So plus VBE. So the voltage drop between this Q1, Q2, that is the base of Q2 transistor and emitter of Q2 transistor is VBE. And coming to this B point, so E is equal to 0. Is equal to 0. So we are going to write the KVL in this loop. So that is nothing but here we are having only R2 resistor and base emitter junction. So for that reason, we are going to write I into R2 minus I into R2 plus VB is equal to 0. So from this equation, we can write that VB is equal to I into R2. So see here, VB is equal to I into R2. So we have written like that. So then from this equation, we can write I is equal to VB by R2. So as we have written that VAB is equal to I into R1 plus R2, we are going to replace the I value in this equation. So VAB is equal to VB by R2 into R1 plus R2. So VAB is equal to VB into 1 plus R1 by R2. So nothing but VBE multiplier. So here you can see. So this VB, we are going to multiply this resistance value with this voltage across VBE. So because of this, we are going to call this circuit as a voltage multiplier. So with the help of voltage, we are going to multiply it with the resistance. So we are going to call this circuit as voltage multiplier circuit also. This circuit as voltage multiplier circuit. So this is one of the circuit which is going to shift the DC level. So these are the level translator circuits. So these three circuits are the level translator circuits, which is going to use a single resistor and which is going to use a resistance voltage division rule, that is R1 R2, and which is going to use a current mirror. These three circuits, and also we have discussed about the voltage multiplier circuit. So now we are going to discuss about the cascaded differential amplifier. So the series connection of differential amplifier is called the cascaded differential amplifier. So this is nothing but what we have discussed in the that is the first two sections of the operational amplifier is nothing but two differential amplifiers. So how the two differential amplifier is going to combine in an operational amplifier, here you can see in this circuit diagram. So that is nothing but a cascaded differential amplifier. The cascaded means the series connection of differential amplifier is called the cascaded differential amplifier. So two differential amplifiers, so one is a balanced output and another one is unbalanced output. So from this here, from this circuit, you can see that what is the balanced output circuit and what is the unbalanced output circuit. So balanced output means, as we have studied that, so balanced output means dual input balanced output means here we are going to give the input to the two transistors, base of two transistors same. So here you can see that. So we are in the first stage, we can see that the input is given to the two transistors. So this is dual input. So if the output is going to take between the collectors of two transistors, then it is said to be balanced. So here you can observe that we are going to take output across the two collectors of two transistors. So this is one of the transistor and this is another transistor. So we are going, so we can say that this is a balanced output. So the first stage is nothing but the dual input balanced output differential amplifier stage. And coming to the second stage, here we are going to give the output of the first differential amplifier to as the input of the second differential amplifier directly. This is called DC coupling. So as we have studied the DC coupling, so because of this DC coupling, so there will be a DC shift, there will be a DC transfer between one stage to another stage. So because of that, we have introduced a level shifter, as we have discussed now itself. Now here you can see that we have combined directly these two circuits. So in the second circuit, you can see that it is a dual input. So here also we are giving input to the basis of two transistors. Here also we are giving the input to the basis of two transistors, you can see in the second stage also. But here you can observe one thing, that is the output is going to be taken at the collector of only one transistor. So when we are going to take output at the collector of one transistor, then it is said to be unbalanced output. So the first stage is nothing but the dual input balanced output. and differential amplifier, and the second stage is nothing but the dual input unbalanced output differential amplifier. So here this is the cascade differential amplifier. So the main requirement for the successful operation is perfect matching of the transistors. So the transistors what we are using in differential amplifier must be perfectly matched uh, of the transistor and resistance values. Here we use transistor arrays like CA3086 and LM3146 ICs. So we are going to use these for this cascaded differential amplifier. So this is about the cascaded differential amplifier. So now we are going to discuss about the last stage in an operational amplifier, that is push-pull amplifier. So now you can see here the output stage. So the output stage in an operational amplifier is a push-pull amplifier. It must be having the that is the output stage means here the output stage must be having so many applications, that is it must have high gain, it must have high amplification factor, like that we have to choose. So the output stage of an operational amplifier is a push pull amplifier, so for that reason we have used here a push pull amplifier, so which possesses a large output voltage swing, and which is having low so low output impedance, and low quiescent power dissipation. So low power dissipation, nothing but so when coming to this is the circuit what we are using the output stage. So this is a push pull amplifier. So here one of the transistor is NPN transistor, another transistor is a PNP transistor. So NPN and PNP both we are going to use here. So which in which one transistor is going to push the output and one transistor is going to pull the output. So because of that action, this circuit is also called as push pull circuit. So when Vin is positive, so here coming to the operation of the circuit, when input signal is positive, the Q1 is going to be in on state, and when Vin is negative, Vin possesses a negative cycle, then Q2 is in on state. Q1 is on, supplies the current to RL resistor. When Q1 is on, Q1 supplies the current for a RL resistor, and when Q2 is on, Q2 is going to supply the current for the road resistor RL. So in this way, it provides a amplified output. So however, this is having a drawback, that is the limitation is crossover distortion. So see here that crossover distortion is nothing but so this transistors is not going to conduct, as we know that this is non-linearity property of the transistor. So up to zero point 0.7 volts, that is zero point 0.7 volts, the transistors are not going to conduct. So because of this reason, there will be a possibility of getting distortion. So this is called crossover distortion. So the output voltage V naught remains. That is, the crossover distortion is nothing but the output voltage V naught remains at 0 volts until it exceeds VB is equal to zero point 0.7 volts. So this can be eliminated. This also can be eliminated. So by applying a bias voltage V slightly greater than 2B. So by applying some bias voltage, this can be eliminated. By applying some bias voltage slightly greater than 2 VBE between the two bases of the transistors. In quiescent conditions, also a small amount of current flows. So VBE multiplier. So here you can see this. So this circuit, this is the modified circuit. So here we are going to use a voltage source such that it keeps the two transistor bases which is greater than zero point 0.7 volts. The emitter resistors R1 and R2 stabilizes the quiescent base current. So this emitter resistors is going to, this R1 and R2 is going to stabilize the base current. So this is about the output stage of operational amplifier. So as we have discussed that operational amplifier constitutes four blocks. The first block is a differential amplifier circuit, and the second block is a differential amplifier circuit, and the third block is the level shifter circuit. So as we have discussed that about the level shifter, and the fourth block is nothing but the push-pull amplifier circuit. So these four configurations up to now we have discussed about these four configurations, and now another differential amplifier we can see, that is the
in the place of bipolar junction transistors. Up to now we have discussed about the bipolar junction transistors. Now we are going to replace the bipolar junction transistors with the field effect transistors. So why we are going for field effect transistors means, as we have discussed it, that if the input resistance is high, then there will be a improvement in the CMRR, the common mode rejection ratio, and also the improvement in the differential gain. So because of that reason, as FET is having a high input resistance when compared with this BJT, so we are going to use this FET instead of BJT. So which is that is the one of the reason we are going to consider this FET. So here you can see that by using this FET, the input resistance of a differential amplifier is in the order of the 10 power 9 to 10 power 12 ohms. So which is having a high resistance value. Here you can see that. So the as the input resistance of FET is very high, the differential amplifier input resistance will also high by using this field effect transistors. So whereas the limitations of field effect transistors is low voltage gain and higher offset voltage. So these are this FET is also having some limitations, that is a low voltage gain and higher offset voltage. So AC analysis. So AC analysis, RC is replaced with drain resistance RE, and RE is equal to small RE is equal to 1 by GM, that is conductance. GM is nothing but here conductance. RE is emitter resistance. So AD is equal to RC by RE, RD by 1 by GM, and GM. So AD is equal to GM into RE, that is the conductance into the drain resistance. So that depends upon the AD is going to depend upon here the conductance and the drain resistance, you can see. So this is the differential amplifier, FET differential amplifier, field effects transistor differential amplifier. So RC is replaced with the drain resistor RE, and here input resistance RS1, and the gate resistance we are considering RG, the gate resistance. So here also you can see this RS2 and RE. So VS1, VS2 are the supply voltages, and in the place of this source resistor, we are going to use as a constant current source using diodes. So as we have discussed in our last classes, this constant current source using diodes. So here we are going to use this circuit for for providing the constant current source. So this is about the FET differential amplifier. Next, we are going to consider the ideal op-amp parameters. So coming to the op-amp parameters, up to now we have discussed about the internal structure of the op-amp. That is, we have discussed about the first stage, second stage, third stage, and the fourth stage. The first two stages are differential amplifiers, and third stage is level shifter stage, and fourth stage is push-pull amplifier stage. And coming now, we are going to discuss about the operational amplifier parameters. What are the parameters that operational amplifier constitutes? We are going to see, and if it is an ideal op amp, what how the parameters will be. So here the AOL is nothing but open loop. OL means open loop. So open loop voltage gain. So open loop voltage gain is how the open loop voltage gain of the op amp will be. So this is the op amp symbol. So you can see with the help of a triangle, we are going to show this operational amplifier. So which is having two inputs, V1 and V2. So the differential voltage is nothing but VD. So I1 and I2 are the currents entering into the operational amplifier. So and AOL is the voltage gain of this operational amplifier. So V0 is the output voltage. So for an ideal op amp, we are going to consider AOL must be infinity. So AOL must be very high. Open loop voltage gain must be very high. That is infinite. So whereas coming to the input resistance, that is the input resistance. That is the input resistance of the operational amplifier must be infinity. So which ensures, which says that op amp input terminals does not draw any current. So no current flow into the operational amplifier. So R naught output resistance is almost zero. Output resistance is zero. So the output voltage must remain same irrespective of the value of the load resistance. So this shows that output resistance remains same irrespective of the value of the resistance. And some of the other characteristics we are going to see here. So VIOS, input offset voltage. IOS means nothing but input offset voltage. Input offset voltage. So zero offset voltage. VIOS is always zero. The presence of small output voltage. What is this offset voltage? Is nothing but the presence of small output voltage through V1 and V2 are 0 volts. Although the V1 and V2 are 0, there will be a small output voltage. This is called nothing but offset voltage. So this offset voltage must be 0. For an ideal operation amplifier, there will be no offset voltage, but practically there will be some offset voltage. So for ideal operation amplifier, this offset voltage must be 0. And coming to the bandwidth must be infinite. So because at any frequencies the op amp must work, the op amp must possess a maximum gain. So from 0 hertz to maximum hertz, maximum frequency, the op amp must possess the same gain, the unity gain. For an ideal op amp, the gain of the op amp will be constant from 0 to infinite frequencies. So the op amp amplifies the DC as well as AC signals. So zero frequency signals are nothing but DC signals. So bandwidth must be infinite. So next is coming to the CMRR. CMRR row, which is infinite. CMRR must be very high. So for ideal op amp, CMRR must be infinite. This ensures that zero common mode gain. There will be no common mode gain. So CMRR infinite means the common mode is almost zero. Sleeve rate. Sleeve rate means a change in the output voltage occurs simultaneously with the change in the input voltage. So this is nothing but the sleeve rate. The sleeve rate must be also infinity. So that is sleeve rate is given by dV naught by dt must be maximum. So for an ideal op amp, this must be infinity. Next, power supply rejection ratio or supply voltage rejection ratio. So PSRR or SVRR. So it must be 0. So what is PSRR means? It is defined as the ratio of change in the input offset voltage due to the change in the supply voltage, keeping other power supply voltage constant. So which is nothing but it is defined as the ratio of change in the input offset voltage. It is to the change in the supply voltage. If supply voltage changes, there will be a change in the offset voltage. So the ratio of input offset voltage to the supply voltage is nothing but PSRR or SVRR, supply voltage rejection ratio. So this must be for an ideal op amp, this must be 0. So these are the characteristics of operational amplifier. So with this, so our first unit has been completed. So in the next class, we are going to recall once again, we are going to recall about all the topics and we are going to start our second chapter. Thank you, students. Thank you, one and all.